Hello everyone, thank you for watching this video, and also thanks to Anier Soria for inviting me to participate in this congress. My name is Luis Enrique Garza. I work at Universidad de Colima in Mexico, and my area of research is orthogonal polynomials. And this talk will be about some recent applications related to the stability of linear systems. So this is an outline of the presentation. It is partitioned in 5 parts. The first one deals with basic aspects of the theory of orthogonal polynomials. The second one also deals with basic aspects of Hurwitz polynomials. Then the third section is about the relation between orthogonality and stability. In particular, how can we construct Hurwitz polynomials by using orthogonal polynomials. And then those results will be used in section 4 to study an application of these polynomials in the study of robust stability, and I will finish the presentation with some references. Okay, so for orthogonal polynomials, probably some of you know that the first examples appeared late in the 18th century. The first examples were the classical orthogonal polynomials, for instance, Jacobi, Laguerre, Hermite. But the general theory started in the 19th century with the works of Chebyshev, Markov, Stiglitz, and many others. The most known cases, the most useful cases, are the so-called classical families that I mentioned before. This is Jacobi and its particular cases, Gegenbauer, Chebyshev, Legendre. Also the Laguerre polynomials and the Hermite polynomials. So there are many people around the world studying orthogonal polynomials, and we can more or less always classify them in two main theories. The first one is when the orthogonality measure is supported on the real line. In that case, we call those orthogonal polynomials on the real line. And orthogonal polynomials on the unit circle are when the orthogonality measure is supported on the unit circle. There are also several generalizations. Matrix orthogonal polynomials occur when you consider a matrix of measures, and the corresponding orthogonal polynomials have matrix coefficients. We also have polynomials in several variables, and also multiple orthogonality when you have orthogonality with respect to more than one measure. There are, of course, many applications and interrelations of orthogonal polynomials with other areas. In particular, orthogonal polynomials are very closely related with the theory of continuous fractions, the moment problem, approximation theory, and special functions, in particular hypergeometric functions. And they also have a lot of applications. I'm just going to mention some of them. They're well used, it is well known that they use in the development of quadratic formulas. They also have applications in mathematical physics, probability theory, signal theory, digital image processing. And the one that is related with this presentation is an application in control theory, in particular, in the study of the stability of certain linear systems. Now let's start. This talk deals mostly with orthogonal polynomials on the real line. So in this case, we consider a positive measure mu, which is supported in some interval of the real line that we will denote by E. If we have those two things, then we can construct an inner product in terms of the measure in the usual way, and we will say that we have an orthogonal polynomial sequence Pn if these orthogonality conditions are satisfied. Right? So this, of course, by using, if this is an inner product, by using the Gram-Schmidt orthogonalization process, we can always guarantee the existence of a sequence of orthogonal polynomials, right? And this is true for any measure, but in particular, if the support of the measure is not bounded, we require these integrability conditions on the measure, that the integration with respect to all of the monomials is a finite number. So these numbers here are called the moments associated with the measure mu. Now, if we take those moments and we construct what is called the Grand matrices, these ones, this is the truncated case, These are called Hankel matrices because they have the property that all of the anti-diagonals are constant. So in the case that these are the moments associated with a positive measure, then these matrices are positive definite for every n. These ones, right? We also have a converse result. If you have an arbitrary sequence of numbers, you can ask yourself if it is possible to find a measure mu such that those arbitrary numbers that you have are precisely the moments of the measure, right? So the answer to this question is yes, and you can take any arbitrary sequence as long as they satisfy these positivity conditions, right? So we have a necessary and sufficient condition of the moments that guarantee the existence of a measure, and of course the existence of a family of orthogonal polynomials with respect to that measure. There are another family of polynomials that we will use in this presentation. They are called the second kind polynomials. They are defined by this expression. This is the integral of this thing with respect to the orthogonality measure. Of course, by the construction, it's very easy to see that Qn is a polynomial in the variable x of degree exactly n minus 1. Now, it turns out that these polynomials, the orthogonal polynomials and the second kind polynomials, they have some very interesting properties in relation with the zeros. In particular, it is well known that the zeros of each orthogonal polynomial, Pn, are simple, are real, and they are located in the interior of the convex hull of the support of the measure E. It is also well known that the zeros of two consecutive polynomials interlace. That what this means is that between any two consecutive zeros of Pn, you can find exactly one zero of Pn minus 1. And this interlacing property is also satisfied between the zeros of Qn and Pn, and also the zeros of Qn are simple and are real. And it is also known that this rational function, the second kind polynomial and the orthogonal polynomials, they appear in Padé approximation. Now, another well-known property of orthogonal polynomials is the following. Given an orthogonal sequence, they satisfy a three-term recurrence relation of this form, right? Where these numbers, bn's, are real numbers, and these an's are positive numbers for every n. Notice that both the orthogonal polynomials and the second kind polynomial satisfy the exact same recurrence relation with the exact same coefficients, except that they have different initial conditions. Right? For the orthogonal polynomials, we define the polynomial of degree minus 1 that appears here by 0. And since this harmonic, the first one, the degree 0 polynomial, is equal to 1. But the initial conditions for the second kind polynomials are different. The first one is equal to 0, and Q1 is just a constant, because remember that the degree of Qn is just n minus 1. Right? So of course, this relation represents the operator of multiplication by x with respect to the basis of polynomials. So if we compute the matrix associated with that operator, is this well-known Jacobi matrix. In the main diagonal, we have the terms b, these ones. In the subdiagonal, we have the a's. And in the upper diagonal, we have 1 because we are talking about harmonic polynomials. So this matrix is called the Jacobi matrix, and it represents the operator of multiplication by x. Of course, this is the monic normalization, and this matrix has this form. But if we consider orthonormal polynomials, then this matrix is symmetric, and of course, in that case, the operator will be self-adjoint. We also have the following inverse theorems. Given arbitrary sequences of numbers an's that are positive and numbers bn's that are real, if I construct a sequence of polynomials by using this recurrence relation, right, with these arbitrary numbers, then the sequence of polynomials that we obtain is orthogonal with respect to some positive measure. And this is called the Favart theorem. Right? Another theorem which is important is that given any two polynomials of consecutive degree, let's say degree n minus 1, with real, simple, and interlaced zeros, we can guarantee the existence of a sequence of polynomials up to degree n that is orthogonal with respect to some measure. Right? So as a consequence of all of the properties that I mentioned of orthogonal polynomials, we have the following equivalence relations. We can have a sequence of moments satisfying the positivity conditions on the Hankel matrices, and they are equivalent to the existence of a positive measure which is supported in some interval of the real line. Of course, the existence of this measure is equivalent to the existence of an orthogonal sequence. And of course, because of Favart theorems and the three-term recurrence relation, then the existence of this sequence is equivalent to the existence of two sequences of numbers. These ones are positive and these ones are real. Okay? So this basically means that if you start with any of these objects, you can determine the other three. Right? So they are equivalent in that sense. Okay, so that's everything with respect to orthogonal polynomials. Now, let me say something about Hurwitz polynomials. So the motivation for the study of Hurwitz polynomials is the following. We consider the following continuous time invariant linear systems, which are represented by this expression. Of course, this can be seen as systems of differential equations of order 1. And it is very well known in this situation. A is a square matrix of size n. This vector in Rn is the vector of solutions. And it is very well known that the solutions for this type of systems they have this form, right? So they have exponential type. And these exponents that appear in the exponential are precisely the eigenvalues of the matrix A. That is the same that saying that these lambdas are the roots of the characteristic polynomial of the matrix A. Right? So this gives this motivates the following definition. We will say that the linear system, this one, right, will be asymptotically stable or exponentially stable if the limit when t goes to infinity of the solution goes to 0. Now, because of the form of this solution, if we want that to be asymptotically stable, I mean, if we want the limit of this x to go to 0 when t goes to infinity, of course, we need that this lambda, they have negative real part. So basically, the next definition says that a polynomial with real coefficients will be a Hurwitz polynomials if its zeros, see, the roots, belong to the left half plane of on the complex plane, so the left side, right? They have negative real part, right? So basically what we are saying is that a linear system of this form will be asymptotically stable if and only if all the eigenvalues of the matrix A have strictly negative real part. In other words, it will be asymptotically stable if and only if the characteristic polynomial is a Hurwitz polynomial. So this motivates the study of Hurwitz polynomials, right? So basically, the two main problems when considering this stability issue is that we need to find some methods to characterize the stability of a given system, and of course, related to that we need to determine if a given polynomial is stable without explicitly computing the zeros. Right? So there are many criteria for determining if a given polynomial is Hurwitz or not. Right? The most famous are these two, the root Hurwitz polynomials that depends on the determinants of some matrices that we construct with the coefficients of a given polynomial. And we also have the stability test that basically what it does is that given any some polynomial of degree n, you do some operation and reduce the degree of the polynomial to n minus 1, and the result says that the first polynomials is Hurwitz if and only if the lower degree polynomials is also Hurwitz. So that basically means that gives you a method when you are systematically reducing the degree of a polynomial until you get to degree 1. And then you check that last polynomial, if that last polynomial is Hurwitz. If it is, then every other polynomial in the sequence, and in particular the first one, will be Hurwitz. So those are the two main theorems to characterize the stability of a polynomial without explicitly computing the roots. But there are other two criteria. The first one is the Hermite-Billier theorem. The second one is what I'm calling the Markov's parameter theorem. These two are very related with the contents of this presentation, and that's why I will talk about them in more detail. Right? So the first one is the Hermite-Billier theorem. It says that given any polynomial with real coefficients, for this one, in this case this polynomial has even degree, we can decompose that polynomials as follows. Right? We can decompose as the sum of an even polynomial and odd polynomial. Right? So h is the even part of the polynomial, and it is defined with the coefficients of the even powers of f, this one. And g is constructed by using the coefficients of the odd powers of f. So that means that h is the even part of f and g is the odd part of f. So of course, if f has even degree, then this polynomial has degree n and g has degree at most n minus 1. And of course, if our initial polynomial has degree to n plus 1, then you can consider a similar expression, but now this polynomial will have degree n, and this polynomial will have degree at most n. Right? So the Hermite-Billier theorem says that if you take any real polynomials and you apply this decomposition, then that polynomial will be Hurwitz if and only if the even part and the odd part have simple negative and interlacing zeros, and their leading coefficients, they have the same sign. So basically, the Hermite-Billier theorem says that you can decide about the Hurwitz character of a polynomial by verifying an interlacing property of the zeros of the even and odd parts of that polynomial. And of course, this, we remember from the previous sections that this is a property that orthogonal polynomials have. Right? Okay, the other criteria is what I'm calling the Markov parameter theorem. In this situation, you take another real polynomial, f, and you apply the same decomposition that I mentioned before, right, in terms of the even part and the odd part, right? Now we consider the following expansions, right? So we consider the Lorentz expansions of these rational functions, right, which is this one. Of course, if g and h, if g has degree n minus 1 and this has degree n, of course you have your expansion starts with this term. But if they have the same degree, then you have a constant factor here, right? So this happens in the even degree case, and this happens in the odd degree case. Right? So the numbers, the coefficients that appear in the expansion, are called the Markov parameters. And the theorem says that a polynomial f is Hurwitz if and only if the Hankel matrices that are constructed with the Markov parameters are positive definite. Right? For the odd degree case, it is also required that the first moment that appears here, which is this one, is also positive. So basically what I'm saying is that the Markov parameter theorems characterizes Hurwitz polynomials in terms of the positivity of some Hankel matrices, which is something that also happens, as you probably remember, with orthogonal polynomials. Now, since we are looking at a lot of connections between Hurwitz polynomials and orthogonal polynomials, of course, there should be a relation between the two theories, right? And the first thing that I want to point out is that the connections between stability and orthogonality are very well known. The first thing is a connection with stability with the moment problem in continuous fractions, which are subjects that are very related to orthogonal polynomials, and this is included in a book by Ganmacher in 1959. There are also another contribution from the 90s, from Jenin, that talks about the relation between the Euclid's algorithm, orthogonal polynomials, and the Routh-Hurwitz algorithm. So basically what I'm trying to say is that the relation between orthogonal polynomials and Hurwitz polynomials was known by many people. But as far as I know, I think it has not been exploited recently, right? So basically the main result is the following. We already discussed that the property of having simple and interlaced zeros is a property that both the even and odd parts of a Hurwitz polynomials and the orthogonal polynomial and the second kind polynomials share, right? So these guys and these guys, they both have this property. And also for the positivity of Hankel matrices, of course we know that this is true for the orthogonality when the Hankels contain the moments, and this is also true for the even and odd part of a Hurwitz polynomials in terms of the Markov parameters, right? So of course we have these connections, so we know that something is going on, and there should be a relation between orthogonal polynomials and Hurwitz polynomials. So the relations is as follows. This is a very explicit relation that is not in the previous contributions that I mentioned. I'm only going to mention the even degree case because the odd degree case is very similar, although a little bit more complicated. But the theorem says the following. It establishes a relation between Hurwitz and orthogonal polynomials in the even degree case. We consider a polynomial, which is Hurwitz, and we apply the decomposition that we mentioned before, right? This is the even part, this is the odd part, right? Now, with the even part, I introduce this change of variable and I define a polynomial Pn. And with the even part, the odd part, sorry, I introduce this change of variable and I define another polynomial Qn. Well, it turns out that Pn is orthogonal with respect to some measure supported in the positive part of the real line, and Qn is the corresponding second kind polynomial, right? So this basically means that if you have a Hurwitz polynomials and you decompose it into the even and odd parts, the even part is an orthogonal polynomial and the odd part is a second kind polynomial. There's also a converse result. If you take any sequence of orthogonal polynomials with respect to some measure positive that is supported in the positive real line, right, then you construct the second kind polynomials with the formula that I showed before, and you construct this polynomial in this way, right? So you construct a polynomial of degree 2n by using Pn and Qn. So this polynomial will be Hurwitz of degree 2n. And of course, the Markov parameters of this polynomial are precisely the moments of the measure, right? So this allows you to establish a one-to-one correspondence between orthogonal polynomials and Hurwitz polynomials, right? And the part that we will use is precisely this one. We will construct sequences of Hurwitz polynomials by using orthogonal polynomials. So some other comments that I want to make in relation to this is that I already mentioned this. A similar result can be obtained for Hurwitz polynomials of odd degree, but there's a free parameter that appears, right? But other than that, it's pretty much the same idea. And of course, if you have a whole sequence of orthogonal polynomials and you start constructing polynomials with this formula and with the corresponding formula for the odd degree case, then of course you can construct a whole sequence of polynomials of every degree that they will be Hurwitz, right? And as long as your measure is supported on the positive part of the real line. And we also prove in this contribution is from 2019, that if you construct a sequence in that way, then that sequence satisfies a three-term recurrence relation, which is similar to the relation that the orthogonal polynomials satisfy, with the exact same coefficients. Right? Also, there's a Favart type theorem for this sequence, right? This basically says that you can take arbitrary sequences an and bn, satisfying some additional conditions, and you can construct Hurwitz polynomials recursively. Right? All of these results can be found in this recent contribution with Noé Martinez and Baltasar Aguirre Hernandez. Okay, so now we go to the last part, which is an application of this connection between orthogonality and stability to the study of robust stability. So let's first talk a little bit about the problem of uncertainty, right? Remember that we have a linear system, right? It has this form, right? This form. But now it happens in real life that when you model some process, then that process has variation, right? That could be because of the nature of the process, or also that you are not able to take precise measurements, and that's why sometimes the matrix that you are considering is not exactly the real matrix. So basically what I'm saying is that there's some variation, and it is useful to introduce that variation on the system. So one way of doing that is that you say that the matrix depends on a vector of d parameters q, which is contained in some domain on Rd. So you have the variables, and you say that your matrix depends on those d variables, right? Of course, if the matrix depends on those variables, then your characteristic polynomials and of course the stability of the system also will depend on those parameters, right? So the definition is as follows. We will say that this linear system is robustly stable if the characteristic polynomial of the system is a Hurwitz polynomial for every value of the parameters, right? So this is of course very important in applications because there's always variation, and you want to guarantee that your system is stable even if your system varies, right? So this vector q is called an uncertainty parameter, right? And there are several types that are considered. So the easiest one is what is called interval uncertainty, right? So in this case, for instance, you can consider a family of polynomials that depends on some vector q, right, in the following way, right? So you have n plus 1 parameters, and each one of these parameters appears as a coefficient in the corresponding powers of the polynomials. And each one of these coefficients is a number that lives in some interval on the real line. For instance, q0 belongs to the interval x0, y0, and so on, right? So of course, in this case, q is an n plus 1 dimensional vector like this, right? And D is a hyperrectangle because all of these are intervals, right? So, of course, the problem of determining if all the polynomials for all the possible values of the q's will be Hurwitz or not, right? And there is a theorem that allows you to determine the stability of the whole family in terms of only 4 polynomials. So the theorem is the Kharitonov theorem, and it says that every polynomial in the family, I mean these polynomials for every possible value of q, is Hurwitz if and only if these 4 polynomials are Hurwitz. And notice that these 4 polynomials are defined by taking extreme values of the parameters, right? And so on, right? So basically these 4 polynomials characterize the stability of the whole family, right? This is what they call interval uncertainty, right? Of course, there are more general types of uncertainty. We have affine uncertainty when the coefficients are linear combinations of the q's, for instance, like this one or this one. We have multilinear uncertainty when the coefficients are linear in some variable, but with the other variables fixed, for instance, this one, right? So you allow products, but you don't allow powers greater than 1. Then you have the polynomial uncertainty, where the coefficients are multivariate polynomials in the parameters Q. For instance, in this case, you also have products, but you allow to have powers bigger than 1. Right? Of course, the more general is your uncertainty, the more difficult is to characterize the robust stability of your system. Right? And there are only theorems in the case that affine uncertainty and interval uncertainty. And for instance, for multilinear and polynomial uncertainty, there are no general theorems to decide whether the whole family is Hurwitz or not. Right? So with this in mind, we proceed with the application on the study of robust stability by using classical orthogonal polynomials. And the idea is the following. The idea is you take an orthogonality measure, right, and introduce a parameter t. For instance, this is the Laguerre measure, right? And in terms of this Laguerre measure, we introduce a parameter t that we are gonna put here. I'm gonna insert it in the exponential, right? Of course, the positivity of the weight is not affected, right? But now the measure depends on the variable t, which means that the corresponding sequence of orthogonal polynomials and the corresponding sequence of second kind polynomials will also depend on t, but they will be orthogonal in second kind for every value of t, right? Since this is orthogonal and this is the second kind for every value of t, I can apply the formulas that I mentioned in the previous section, and I can construct sequences of Hurwitz polynomials by using the orthogonal polynomials. But now the thing is that the Hurwitz polynomials will also depend on the variable t, right? And because for every value of t, these are orthogonal, and these are the second kinds, then everything that I construct is robustly stable for every value of t, right? For instance, if I take the Laguerre polynomials and consider the particular case that alpha is equal to 0, this is if you construct the Laguerre polynomial of degree t, of degree 3, then you have this expression. Notice that the t appears here in the coefficients. I have powers greater than 1, so basically what I have is polynomial uncertainty, right? So with this polynomial and the second kind polynomial, I can construct a Hurwitz polynomial. The coefficients, we have polynomial uncertainty, but I know it will be robustly stable for every value of t. So that's pretty much the idea. Some other observations are the following. These have applications in control design, in particular in a technique that is called the pole placement. So basically what you do is, if you have a system that is not stable, you propose a compensator, right? And you try to introduce something into the system in such a way that the final characteristic polynomial is a pre-designed polynomial. So for instance, if you know that the polynomials constructed by using orthogonal polynomials are robustly stable for every value of t, you can propose those polynomials for pole placement, right? So they can be used in the design of control systems, right? They are also useful in the study of the stability of PID systems. This is proportional integral and derivative controllers, which are very well known and very useful in industry. Of course, I just presented an example with the Laguerre measure, but we can of course use other measures, for instance Jacobi, right? In this contribution from 2019, we do the analysis for the Laguerre measure in the Jacobi measure. Of course, instead of introducing just one parameter t, we can introduce more parameters, right? In this contribution, we also analyze the behavior of the zeros with respect to t, right? So we obtain some equation of motions of the zeros when you vary the parameter, and that is also important in the applications. Of course, depending on how you introduce the parameter, you're gonna have different types of uncertainty structures in your polynomials. Right? So to finish, I'm just going to mention some other applications. We are currently considering other applications such that the study of stability of control systems with delay, right? So when for some reason you have to introduce a delay on the system, then the study of the stability changes. But it is also possible to use orthogonal polynomials to design compensators so that you guarantee that your system is stable for every value of the parameter and within some range of delay, right? Another thing that we are considering right now is the fact that you can construct robustly stable families with orthogonal polynomials by using recurrence relation, right? Remember that what I showed before is that is basically what we're doing is you modify, you perturb the orthogonality measure, and the resulting polynomials will depend on the parameter, right? But there's another way of doing this, and this is something that we are currently studying, that we can construct Hurwitz polynomials by using recurrence, right? The other thing is that there's also analogous results for discrete linear systems in terms of orthogonal polynomials on the unit circle, right? And this is something that we are looking into. And just to finish, I just want to point out that this is a joint work with the Electric Engineering Department at Universidad Autónoma de Tamaulipas in Mexico. So in this work, there are some people that are mathematicians and there are other people that are engineers, and we are working together to try to use more applications of these polynomials. Just to end this presentation, there are some references. This is the classical book on orthogonal polynomials by Sego. This is a very good reference in robust control by Bhattacharya. The results that I presented here are included in these papers. This paper in linear and multilinear algebra from 2019, and this paper of mathematics in 2019. There's also an application. This is very recent in plans with delay. If you are interested in that, you can. This article is open access, so you can find it on the web, and you can learn a little more if you want. That's all. If you have any questions, please, my contact information, I assume that it will be published in the website of the conference. So if you have any questions, please send me an email and I will try to answer you. And that's it. Thank you very much.